Hello, my name's Dan Green. We're doing another ICQ Comets and Their Cousins YouTube channel recording here. We have an interesting panel today, nine of us. So we have our regular team members, myself, Dan Green here in Massachusetts, and Casper and Carl are in Arizona, Mike is in Germany, and Dennis is in Scotland. Then we have four additional panelists today. We have Qicheng Zhang is from Lowell Observatory. He's a postdoc there and studies comets. We had him on our last video as well. New to our video is Bill Gray, an independent researcher working on orbit determination for comets and asteroids. He's been working on analyzing the quite large backlog of sun-grazing comets found over the last couple of decades through SOHO. Dr. Joe Marcus has an MD from Washington University in St. Louis. He's a retired surgical pathologist, an amateur astronomer. In collaboration with McDonald Planetarium in St. Louis, he founded Comet News Service in 1975 and was editor over its lifespan, ending in 1986. He continues to be active in cometary astrophysics research, publication, speaking, having devised models of the psychophysical artifacts affecting visual magnitude estimates and forward scattering enhancement of cometary brightness. Nicolas Lefedo, is that how you pronounce your name? A French optical engineer and amateur photographer, is passionate with physics and optics. After 2 years studying mathematics and general physics, he specialized in optics and related field sensors, imaging processing, etc., for 3 years at the Institut d'Optique, from which he graduated in 2006. His first job was in California on polarization imaging and image processing. Then he worked in optical metrology and adaptive optics for ultra-intense lasers. Today, he works in the field of high-resolution biomedical imaging. His hobbies are photography, astronomy, optics, atmospheric phenomena, and image processing. Okay, so we're here today to talk about a new, interesting, very interesting sun-grazing comet. Has a designation C slash 2026 A1 and has a name MAPS. MAPS is all capital letters, MAPS. It comes from an acronym for the discoverers. It was found by Alan Maury at San Pedro de Atacama in Chile, where he has an observatory, personal observatory that he sets up, and they do a survey there. And he has four amateur astronomers in France that help him. And the acronym MAPS comes from the last names of all those observers. And I will be posting this on over our discussion here later, so you can see all the names involved. So the comet that he found was on images taken with a Schmidt telescope, 20 centimeter Schmidt, on January 13th of this year. So he saw it as a comet, and it went to the Minor Planets PCCP webpage. Eventually got announced when there were enough confirming observations. Sam Dean, an amateur in Simi Valley, California, found pre-discovery observations in Atlas images going back to the middle of December, which for political reasons are still not accepted by the Minor Planet Center. So the Minor Planet Center is missing almost a month of arc. So the orbits that we are using do include the observations that Sam found and measured in the Atlas data over several nights in December and again in early January that were all pre-discovery observations. The comet has been slowly brightening as expected since its discovery in January. So its orbit was early on seen to be that of a Kreutz sungrazer. And we're going to talk today about what Kreutz sungrazers are. But they basically have a retrograde orbit. They go in orbit around the sun in directions different from the planets going around the sun, the opposite direction. And this particular comet has an orbital period of about 1,740 years as of as of the calculations done yesterday with the latest observations by Soichi Nakano. Um, so the interesting thing about Kreutz Sungrazers is that they can be among the brightest comets. They appear to have been, we see many Kreutz Sungrazers, and they appear to all be split off from some massive progenitor comet, perhaps thousands of years ago. We don't really know. There are a lot of studies that have been going on in that regard. So I'm going to stop talking and turn it over to other people in the panel, and we'll start with Joe Marcus, who recently gave a talk on this very comet in St. Louis. Joe?
Okay. I'll try to go through these pretty fast.
Share first.
And let me share the screen.
Share. Oh, wait, sorry, that one. That one. Share.
Can you all see it?
Yep.
The screen should be there. The history, very briefly, is Heinrich Kreutz was the first really to show the orbit of this family of comets, 1843 and 1882. Brian Marsden took up the cause in the middle 1960s and established two population groups. And by far, most of the work, the amazing work really, has been done by Zdeněk Sekanina. And as Dan just mentioned, there's a progenitor comet shown here with many different scenarios that change as the data and the history becomes refined. One of the most significant comets was, and probably the progenitor, if I understand Zdeněk correctly, is Aristotle's comet of 372 BC, orbit period of about almost 800 years. The historian Diodorus Siculus said the torch had such brilliancy and its light such strength that it cast shadows on the Earth similar to those cast by the moon. In Zdeněk's most recent paper, there is the strong suggestion that the comet of 363 AD is a return of Aristotle's comet, and both of these comets must have been extremely large. This comet was sighted in daylight, and with a suggestion that there were multiple comets near the sun at that time in the historical literature. Now, one of Zdeněk's most interesting ideas came about 3 or 4 years ago, in which he suggested that the parent comet was a contact binary, such as what we know to exist now in the solar system. Here is the trans-Neptunian Kuiper belt object Arrokoth, visited by the New Horizons spacecraft after it passed Pluto, showing the neck and two major lobes. The New Horizons program really had profound implications for solar system formation. These are planetesimals that are forming into binaries and multiple structures. And what's interesting about this is that in Zdeněk's hypothesis, you have the contact binary at the top here, and as it rotates or through some other causes as well, it may split. And if the splitting is occurring near perihelion, the minor fragment B here, being closer to the sun, will have a greater acceleration and may have a much larger orbit period. And this may be a possible explanation as to why Comet MAPS has such a much longer period than the typical 700 or 800 years. And the suggestion that Zdeněk has is that the Comet MAPS may be a small fragment from the three what year was it? Well, the AD appearance of the first offspring of the progenitor. Recent returns include the Great Comet of 1843 D1, the Great March Comet. We were somewhat close to the orbit plane there, so the tail looks rather narrow. And as Nicholas Lefaudu points out, uh, Comet Maps is likely to have a very narrow tail. Another view of the comet of 1843 showing it over the western horizon. Um, the idea being that because the comet is south of the ecliptic plane, our orbit plane, that it's going to be very low and very inclined to the horizon. This comet was visible in broad daylight as well. You can see the sun, and just to the upper right is the streak of the comet in daylight. The largest sun grazer that we've seen in modern times is the Great September Comet of 1882, and is part of some of the earlier photographs of comets. This comet was so bright that it wasn't really hard to capture the comet on film at that time. 1882's nucleus also split, and this offered the first glimmerings that the Kreutz family is indeed a cascading series of fragments of comets of all sizes as they disintegrate and eventually will disappear from our solar system. Probably the most spectacular sungrazer in our recent 20th century history was Comet C. This is a classic photograph of the tail, again, fairly narrow. And Comet Keyasiki, as it came close to the sun, uh, became rather difficult to see. And I'll go into this. It's a little bit controversial as to whether this is a real effect, but I do think that it's real. This was a coronagraph series of photographs taken from Japan. And I looked at Gary Kronk's reports of observations in his Cometography, Volume 5, and plotted what there were there. These yellow data points are actually made by pretty reputable astronomers. There are daylight sightings. They suffer from not having strict comparison objects like Venus in most cases. And to me, the most striking aspect of this figure is that if you look at this line, which is when the comet reached perihelion, just tens of thousands of miles above the surface of the sun, you don't find any observations within a half-day interval around perihelion, even though the comet's light curve was going from -10 magnitude. It should have theoretically gone up to -14 if the comet were if the comet was producing dust. What is probably happening is that the comet is so close to the sun and the grains so hot that they, even though they're silicate minerals, they're sublimating and becoming invisible. Um, the blue part of this curve represents forward scattering enhancement, and the kind of purple part of this light curve is just the usual non-forward scattering counterpart. Um, I took a look at Comet Lovejoy, which is another sun-grazing comet that appeared in 2011, discovered by Terry Lovejoy. And I did something simple and a little bit dirty, I suppose, and I just measured the blooming spikes on the comet's image as seen by the SOHO satellite, and was able to show that it started to depart from an inverse power law, which you see by this straight line. Once it reached about zero point 0.1 AU, where here the logarithm of that number is -1.0, it began to falter, and eventually it began to lose magnitude. So this could be evidence of erosion of the dust grains, making the comet, it looks like 5 or more magnitudes dimmer than it should have been had it been able to follow an inverse power law. I'm going to skip over some of these slides. The brightness represented by I, and the magnitude is represented by uh, the logarithm of this expression, the brightness expression, is a function of the intrinsic size of the comet, I naught, distance from the Earth, inverse square distance, inverse nth power of brightening as a function of distance from the sun, r. And in more recent times, we're now adding in the scattering function, also called the phase function, the phi of theta, and also for the sun-grazing comets, an erosion parameter where the brightness decreases because the grains uh, are sublimating from the heat of the sun. This is John Bortles, a noted comet observer. He published in the International Comet Quarterly the light curves of Comet Pereira, Akayasiki, and White-Ortiz-Bolelli. And interestingly, for this crowd, uh, Comet Akayasiki is intrinsically the dimmest of these three clustered sun grazers, and had the viewing geometry been better for these other comets, they may have been more spectacular than Akayasiki. Here's a summary page of the intrinsic sizes, as we probably best understand them today, of these recent Kreutz sun grazers, where the Great March Comet is 4.9 here. 1882 R1, the Great September Comet, far outshines all of these other comets in the table. Now, Comet Lovejoy may be the paradigm for comet maps, and maybe that could be a point of discussion after I finish these slides. Lovejoy went from 15th magnitude before absolute magnitude before it reached perihelion, and it passed perihelion, and then it died about a day and a half after perihelion through whatever mechanism, thermal or tidal stress. But what's interesting is that its absolute magnitude became 10. I suppose if you integrate the whole brightness of the comet, and it did become which should include the tail in this case, although we ordinarily do not estimate comet brightness with anything other than the head as the M1 estimate. And then we had the last year's about a year ago, Comet 2024 S1 Atlas also started out very faint and had some sputtering, went up to an absolute magnitude of 11, then back to 14 again. Then at perihelion, it died. So then the question all of us will be interested in is what is going to be the story with comet maps. I think its absolute magnitude now is about 10, and if we're lucky, it'll follow a Lovejoy trajectory. Be interested in everybody's opinion as to whether this can survive, even if it survives to perihelion, whether maps can go much further than Comet Lovejoy went. This is a photograph of Comet Lovejoy taken from the International Space Station. So you can see it's it's a rather spectacular comet, even though it's small, somewhat similar to Akayasiki. Here is Lovejoy appearing in the SOHO coronagraph, the C3 coronagraph, and as it rounded the sun, you can see a remnant of the tail, but the nucleus disappeared. The coma around the nucleus disappeared and then started to regenerate as its distance increased from the sun, and it developed a tail afterwards. And maybe Nicholas can talk a little bit about this in the tail simulations that he has for comet maps and whether it might be similar. This is one of Zdeněk Sekanina's papers showing Lovejoy with an intact nucleus in the upper panels here. And then a day and a half or so after perihelion, it lost the central condensation, but it continued onward as a spectacular comet, probably similar to as a headless comet, similar to the comet of 1887, another Kreutz sun grazer. Another view of Comet Lovejoy, this time from, I'm not sure if this is correct. This could be an error. It may be the stereo satellite. I'm just not sure. But anyway, the point to be made is that it after a perihelion, it did reappear. where my cursor arrow is. Oh, here we go. This is the stereo satellite showing a similar effect, the lagging tail disappearing and then reappearing after perihelion with a coma and not yet developing its post-perihelion tail. This is the light curve of Comet Lovejoy, showing pre-perihelion. It's fairly dim, where here you have decreasing magnitudes indicating increasing brightness on the left y-axis. And here we have a fairly respectable comet. Comet 2024 S1 Atlas had nuclear breakup before perihelion and did not survive to put on a show like Comet Lovejoy did. I'm going to skip some of these slides. This is He Chang's recent paper, excuse me just a minute, which established the size of the nucleus through the James Webb Space Telescope as about 0.38 kilometers or so, a very small comet, but about in the same range as Comet Lovejoy. And looking to see which of these comets survive perihelion, we have several classes of comets. The 5,000 or more of the Kreutz comets, these tiny fragments that have been seen only in the SOHO satellite, are generally less than 0.2 kilometers across, and they invariably do not survive perihelion. Atlas was less than 0.6 kilometers and did not survive perihelion. Lovejoy was 0.4 to 0.6 kilometers, and it did survive perihelion, but only disintegrated shortly thereafter. The great Kreutz comets do survive perihelion, but they often split. And Comet Maps is to be seen, but this table puts Comet Maps into context. This is Nicholas Lafadou's diagram, and maybe it would be better if Nicholas would discuss this at some point. Dan, what would you like to do?
Yeah, Nicholas, you want to step in here and just talk about this?
Yes, maybe I have even a new version that might be of interest with the latest. So possibly I can share it.
I'm going to stop sharing.
Okay.
Okay. And I'm going to start sharing. Where is that? Share. And let's start with this. Share. Okay, so that's the latest version. So as Joseph told, the outcome of what will happen with comet maps is what interests us all, and we are just bound to compare it with other comets that we have had. So the idea here is to put all the comets together to display their heliocentric magnitude. So it removes the component that is due to how the Earth is located compared to the comet, just to see how active it was. And we see the main comets that we have several types of Kreutz, like the 8082 comet, which was the biggest, Ikeya Seki, Lovejoy here, and 2024 S1 Atlas, which break up. And we have comet maps here that was discovered much farther than the other comets. It started rather slowly to increase. Then between early February, first half of February, there has been a fast increase, like we are used to seeing this switch on phase for comet maps. And then it has increased regularly after, and since about middle of March, it seems to have been stalling and not getting above magnitude 9 or 10 here. And just lately, like 2 days ago, it suddenly increased again. So maybe I can remove slightly those. Uh, so it's kicking in again, and we don't know exactly what it means. It means something happens. Is it good? Is it not good? It's hard to tell. I mean, what else can I say? Yeah, and for now, the Comet Maps has been in between, clearly above Lovejoy, uh, near S1 that was active at one point, as Lo just said. But for now, it's still notably above Lovejoy. But this big change, whereas it had before kind of a smooth curve, raises questions.
Yeah, so I just note here, Nicholas, from the diagram, one of the very interesting things about 2026 A1 maps is that has by far the record for the earliest discovery of a Kreutz sungrazer, the furthest before perihelion. And you can see that in your light curve here, where you show that Ikeya Seki coming in quite, it's what was it? Something like, I don't remember exactly. Is it like 40 days different, 30 days different? It's on the order of a month further out. So it's been kind of an uncharted territory. The problem with most Kreutz sungrazers that we see, there are the thousands of SOHO pieces of Kreutz sungrazers, but they are very faint and they can't be seen very far from the sun. Uh, so it's very unusual, and of course, those of us who are in cometary science were really interested when this MAPS comet was discovered because it's so far from perihelion, and of course, there's been some excitement as to, does that mean it's going to survive perihelion because it was found so far ahead of time? And the answer to that is no. Uh, it's just that our detectors are better now than they were years ago. Ikeya Seki was a visual comet discovery. In fact, all of these were visual. Of course, Atlas was not. But Lovejoy, did Lovejoy find that visually or photographically? Was that visual?
Photographic.
No, photographic.
It was photographic. Okay. But yeah. So all of the sun grazers before Lovejoy, before his comet, all of them were visual, I believe. And of course they tend to be found very close to the sun. So they brighten up when they're close to the sun, and are not so bright when further away. And Carl, I don't know if this is a good place for you to talk a little bit about the light curve from your recent work.
If I may just say
Oh yeah,
one
sorry.
thing,
Yep.
then yeah, related to what you just said. So you see, with sun grazers, there's this like funny effect in that their vanishing point, or like let's call it sky projected trajectory, is like a spiral, and it's slightly to the southwest of Sirius. And what do we have there? We have the Milky Way. So, for example, big surveys like the one where I work at, or Pan-STARRS, we cannot survey through the Milky Way. The images would be like literally white, because of star saturation. There is one survey that plows right through the Milky Way, and that is Atlas. That is also in big part because they don't reach as faint as CSS or Pan-STARRS. Now, I don't know exactly where in the sky was MAPS discovered. I mean, I know it was discovered in that Kreutz vanishing point, so it must have been close to the Milky Way. So I cannot but wonder, how many Kreutz sungrazer would have been discovered farther out had their vanishing point projected in the sky would not be in the Milky Way. So
yeah. That's a good point. Observational selection is an important point. Yeah. And the plane of the orbit of these Kreutz Sungrazers also gives an observational bias towards northern versus southern hemisphere, depending on what time of the year they come to perihelion.
Right.
Carl, did you want to?
Yeah, let me grab my slides. So what I did was very similar to what Nicolas showed, except this is a little bit more of a subset of all the observations that were made. These are in particular observations that were submitted to the ALPO, the Association of Lunar and Planetary Observers. And these are only V-band images for the most part as well, either visible, naked eye, not naked eye, but either visual eyeball observations or V-band CCD, CMOS type observations. And the top one is just the apparent magnitude, how bright the comet appeared to observers on Earth. And you can see, shortly after the comet was discovered in January, it was pretty faint. It was about an 18th magnitude object. And then it was brightening at a nice clip. And then sometime around the beginning of the year, early January, it kind of kicked into overdrive, started brightening much faster till about mid-February. And then even though it was still brightening faster than the typical comet rate, it continued brightening like that until, as Nicolas mentioned, about mid-March, when it kind of went into what we call a stall, where it stopped brightening quite as quickly. If you look on the bottom plot here, this is the magnitude of the comet, and I subtracted out the distance from the Earth, as well as the distance from the sun. So if you've got an upward slope, that means the comet is actually getting brighter. If you've got a kind of a parallel slope, slope of 0, that means it's steady state. So even though it might appear to be getting brighter to you on Earth because it's getting closer to the sun, it's reflecting more sunlight, it's actually not producing any more dust. And if you were actually to see that slope go down, become negative, then that would mean the comet is actually intrinsically fading. And we have seen that with some comets. And it again shows, you had a nice brightening trend, kicked into overdrive, continued brightening, and then it's kind of gone flat. And if you look really close, I can almost imagine that the comet is kind of rounding off a little bit. That's not necessarily a straight line. There's a little bit of a rounding there until we had the most recent outburst over the last few days. But these magnitudes are for the entire coma. And the coma of this comet, which is extremely gassy, has gotten pretty large. We're talking 5, 6, even 7 arc minutes. And when you're trying to measure a very blue, very large, low surface brightness coma, especially for a comet that every day is getting lower and lower in the sky, so it's not at high elevation, you're looking through a lot of atmospheric extinction, especially in the blue end, preferentially, as well as dealing with bright twilight now. I could imagine that the comet might start appearing fainter just because you're seeing less and less of that coma because the sky is getting brighter, there's more extinction. So to counter that, what I did is I took data that I took as well as data that Terry Lovejoy took with some of our own telescopes as well as a lot of the telescopes at iTelescopes, which has the telescopes in Australia and Chile. And this is a combination of data that was taken with as small as a telephoto lens and as large as a 0.5 meter, 20-inch telescope. And just measuring the brightness in the V-band of the comet within 20 kilometers of the nucleus. So you're not measuring the whole coma, you're not measuring most of the gas, you're really just looking at the very innermost part of the nucleus where it's mostly dust, though of course in the V-band there's still significant gas contamination. And I didn't have the data going all the way out back here. The data kind of starts around this point. So where we had that rapid brightening and then it's kind of a knee as it slows down. So you can see we're coming out at a rapid brightening and then it's nicely stable until about March 8th or 9th. And then we see the first outburst where all of a sudden the comet got a little brighter. You see it pop up in brightness. And either that's the beginning of this stall phase where it just kind of flatlines for the most part, or I can imagine that, it's brightened, it falls back down, and maybe it continues that brightening trend that we see here. And this is about March 16th now, and now it's gone flat. And you can definitely tell, compared to that early run up, which was, February through early March, where it's pretty much a straight line. You got a lot more wiggles and bumps, which means there's little outbursts going on in here. And then over the last 2 days, as Nicholas mentioned, there's a major outburst of which we seem like we've seen the peak of that outburst because data just from last night shows that the inner coma has faded, and we're starting to see that in the total magnitudes as well. But what does this mean? Does this mean that the comet, the nucleus is, I mean, the outburst could mean that it's shedding mass. Obviously, it's shedding mass. Does that mean it's breaking up? It's just something for us to discuss here. I will mention that when you actually take the astrometric observations and you produce an orbit for this comet, it seemed to be fairly well behaved until around this time, this March 8th, 9th, 10th. And then all of a sudden the data on this side, since March 8th, 9th, 10th, doesn't quite fit the data, the astrometric data from before that. So it also suggests that something may have happened to the nucleus. Not that the nucleus is necessarily moving, but if it is releasing a lot of dust that's falling back, maybe what we call the optocenter. When you look at the comet, the brightest point now is no longer on the nucleus. It might be shifting backwards if there's kind of a debris trail that's now lagging the comet. So yeah, it does suggest that the comet was brightening much faster than most typical comets do, though it actually was brightening, and this is kind of my version of Nicholas's plot here. When it was brightening at February through March, it was still brightening at almost the same rate that Lovejoy was brightening, though much faster than we saw for Ikeya-Seki. And I threw ISON on here, which isn't a Kreutz, but it's also a Sungrazing Comet, which actually may be the most similar in a way to what we're seeing with MAPS, and that ISON was kind of flatlining with little outbursts interspersed here, and then ultimately it did disintegrate, unfortunately, before perihelion rather than after perihelion, so it never became a brilliant object post-perihelion.
Right, so I'd like to just comment on something you mentioned earlier about how when you measure the comet's brightness, or at least when observers report a comet's magnitude, in theory, they should be reporting the entire magnitude, the entire brightness of the coma, but that is often just physically not possible because often the full coma is just too faint. And that sort of shows up if you also look at like just the diameters of the coma that people are reporting. In theory, since this comet here, it's obviously a very gas-rich comet. It looks visually like just a green ball. In the case of a gas coma, physically, what's sort of truncating the edge of the coma there is actually just the gas molecules, the C2 molecules, that are floating out in space until they get destroyed by the sun's UV rays. And that's a phenomenon that sort of slows down as you move further away from the sun because there's just less UV to go around. And so what that actually means is that the physical size of this gas coma, as it's approaching the sun, as it's actually even brightening, the size of the coma is actually shrinking. And so what this means observationally is that for comets that are far from the sun, like this comet was when it was discovered, that the surface brightness of that gas coma is actually just exceedingly low, extremely low, to where even if you have a very, very sensitive telescope, big telescope, or very dark skies, you often just can't physically see the entire coma. And actually, if you do apply correction for essentially how much of the coma you're actually getting, what you see is actually a lot of that apparent rapid brightening shortly after the comet was discovered, or at least through February. That actually sort of essentially just goes away. And what it turns out is if you track the reported coma diameters that were being reported by observers during the same period of rapid brightening, those coma diameters were very rapidly expanding during this entire period. And what was happening was essentially as these reported coma diameters were expanding, that meant people were seeing more and more of the coma, right up until around March or so, well, beginning of March or so, was essentially when the observable part of the coma caught up to the actual physical size of the coma, at which point, even as the comet got brighter and brighter, you can't see any more of the coma because there's no more of the coma to see, at which point you do see that leveling off. And so this effect doesn't account for any of the outbursts that happened in March. But as it turns out, if you apply the corrections and measure the actual gas production rate, there's actually not that much of a steep slope, or there's not really this sort of sudden onset of activity as you might infer from just looking at the total magnitudes. And a lot of it really is just sort of an observer effect from the fact that, as the comet brightened, you were able to visually or photographically detect more and more of the coma, and which made the comet look like it was brightening actually a lot faster than it was. So I just thought that was sort of an interesting effect that may not be entirely all that obvious.
Has anybody been trying to measure the gas production rates of this comet, or is it just the elongation's too small for most?
I have. This is how I sort of this is how I sort of know that this is the effect that's happening, because the gas production rate curve I see actually has almost sort of the opposite concavity as the total magnitude curve that's being reported, where instead of a sudden brightening at the beginning that is been slowing down, it's actually looked more to me like it started off shortly after discovery fairly level, and then it's had sort of an upward inflection to where it's now basically very rapidly increasing.
Okay, so are you using the Lowell Observatory comet filters, which are kind of like the IHW filters?
Yes.
Okay. Did you have any more thoughts about this, Kachang? About you, I know you have about survival generally, and
yeah. And so in the case of this comet's sort of interesting because part of the one consequence of it being discovered super early is that it was at very high elongation when it's discovered, and much higher than like any other Kreutz that's ever been seen. And that's basically let us, as was mentioned earlier, let us actually apply for time on the JWST to actually catch it before it drops to too long of an elongation, because that telescope has a very large solar exclusion zone. It can't point anywhere within 85 degrees of the sun. And so basically had a 3-week window from when it was discovered to when it crossed within that line to actually observe it with that. And the reason, well, one of the reasons that we did that was because in telescopes in space, we can actually get high resolution imagery of the coma, because from the ground, it basically just looks like sort of a fuzzy dot, and you get this sort of ambiguity with any comet where you don't have much resolution of, well, this fuzzy dot is of this certain brightness, but is that brightness mostly from the nucleus, or is that brightness mostly from the dust that the nucleus is ejecting, and maybe the nucleus itself is tiny? And so with high resolution, you can sort of spatially distinguish the two. And so that's what we sort of did there, and how we got that 0.4 kilometer size estimate there. And so the interesting thing about that is that because we now know what the nucleus size actually is, and we have sort of at least rough estimates based on the gas production of the other Kreutz Sungrazers near perihelion, how bright they are. And so from that, we sort of know just how much material roughly we're dealing with compared to the other Kreutz Sungrazers that have been previously observed. And so in some sense, that's taken a lot of the guesswork out of how bright it could possibly get. We know that it's probably not going to get to magnitude -10 because there's simply just not enough material in the nucleus for it to do that. What's most likely the case, given that it's probably on the lower end of estimates for Lovejoy, is that what's most likely going to happen if it were to actually make it to perihelion is that this comet will probably be pretty similarly bright. I mean, similar amount of material, you take it to a similar distance from the sun. As long as it can hold together that far, it should behave fairly similarly. And so we sort of know what at least one possible endpoint is, probably a peak magnitude -1 or so, similar to Lovejoy. If, again, big if it actually makes it to perihelion. One problem, though, of course, is that the nucleus may not actually make it to perihelion in one piece, even if there is enough material, in theory, to survive that passage briefly. It may not necessarily do so. We know of a lot of comets that are about this size or even bigger that are not Kreutz Sungrazers for the most part, that pass nowhere as close to the sun as these sungrazers do. They'll get to say 0.4, 0.5 AU, and very often they'll just disappear into a poof of nothing. And what's most likely happening there is that the outgassing that's driving their brightness, that comes off the nucleus asymmetrically, because the nucleus is not a perfect sphere. And when you have asymmetric outgassing, that can spin up the nucleus. And over time, if it spins up in a coherent direction for long enough, it will surpass first the gravity holding the nucleus together. And if the nucleus has perhaps some sort of strength to it, it can further spin up past beyond the cohesive strength of the nucleus itself. And at that point, the whole thing flies apart. And that's probably one reason why Comet Ison, which was based on most estimates much larger than Comet Lovejoy, why that comet seemed to have just completely been destroyed well before it got near the sun, whereas Lovejoy survived, because Comet Ison, being a dynamically new comet fresh from the Oort cloud, it had a lot of ice very close to its surface that was not, well, presumably not covered by very much rock and debris or whatnot, insulating that ice. And so it had, I believe, a 2-year or so lead time to when it was discovered, or at least the first pre-discovery observation showing it to be brightening happened. So it had been spinning up for basically 2 years, whereas Lovejoy had like a month. And so that effect is something, if it had spun up past its breaking point before making it to the sun, well, now it's not one big kilometer or so size nucleus. It's now a large amount of very small meter size or few meter size rubble. And each of those individually, the survival of those essentially behaves as like meter class comets, which definitely can't make it through a sun-grazing perihelion. So that's one very likely possibility for why those two comets differed in the way they behaved. And so how that applies here is that we sort of have this comet, MAPS is sort of in between those two cases, in the sense that it only turned on, or as far as we know, it only turned on a few months ago, maybe 3 or 4 months ago. So didn't have quite as much time to spin up as Ison, most likely. But on the flip side, it's also much smaller. It's much smaller than Ison, possibly a bit smaller than even Lovejoy. And so now the big question is, and the other factor being that smaller objects, because of their higher surface area to mass ratio, are basically easier to spin up. And so now the question we have here is whether or not that extra few months of spinning up that MAPS has over Lovejoy, is that going to destroy this nucleus before it actually makes it to perihelion? Because if it breaks that nucleus apart and the biggest chunks are only a few meters across, comparable to the SOHO Kreutz Sungrazers, then nothing will survive. It will basically just act like a collection of closely spaced SOHO Kreutz Sungrazers, and all of it will just vanish before perihelion. It will brighten by a lot before it does so, because it will be releasing all of that rock and material all of a sudden dumping it out into space as it's getting vaporized will be very bright in the LASCO coronagraphs, SOHO LASCO coronagraphs, but nothing will make it around the sun, and we won't see anything of it past perihelion. And so those are essentially the two cases I sort of see for this comet. And it could either essentially disintegrate within the next few days before it actually makes it to the sun, or if it makes it to the sun, it will look probably something quite like Lovejoy.
Yeah, Joe Rao put together a diagram with a predicted image of the comet as it goes around the sun, as seen through the LASCO cameras. I believe, I don't know if it was C2 or C3, but I'll put that up here in the video here so that people can see that. Let me ask Bill Gray if he wants to step in here and say something, because he's
I have a question for Qisheng, maybe just as he was talking about his measurement. I don't know if it's the right moment before we switch to another
yeah, that's
thing.
fine. Yep.
Okay. Let me also share. So yeah, the question I have is that we know that so I don't know if you see it right now. That's the famous Halley Comet nucleus images from a Giotto spacecraft. And we know that the comet nucleus, they are very dark, low albedo, while all the small particles that are just outgassing or emitted by the comet, they are very small, so they are very efficient at scattering, and thus they appear bright. So I'm just wondering, is there anything special if we would measure something like this or see the nucleus as Giotto would see? We would probably measure the bright spot and the size of the active area here. I don't know if you see my mouse. The size of the active area instead of the size of the whole nucleus, because it's too dark. So I don't know if there is something special about the wavelengths of the JWST telescope that make this effect not be so strong, or how do you know that you're not measuring just one active area and not the whole nucleus?
Well, so one thing about sort of that image, and you can sort of see that there, is that the active area, it's not just an isolated like bright spot not attached to anything. It's attached to this bright jet of material that's coming out. And what that active area essentially represents is that jet sort of converging, well, going back to the source of the jet, it looks like it converges at a spot on the nucleus. And so, but what happens is that essentially all of that material that's contributing to the brightness of that bright spot eventually, for the most part, well, effectively all of that dust that's making that spot on the nucleus look bright is going to end up in the jet. And you can sort of, it looks fainter because the dust spreads out once it gets into the jet. The jet's not like a laser. The dust sort of diffuses a bit. And but you can sort of account for that, or at least you can model it fairly accurately by essentially just figuring out how bright are each of the jets. Is the dust coming out of the nucleus in every direction? And then you can extrapolate that backward down toward the nucleus. And so part of the advantage we had here was that the nucleus was far, far less active than Comet Halley was in this image. This, I believe, was pretty close to perihelion. And that's one of the reasons to sort of get it early, in addition to JWST not being able to observe the nucleus. Well, not being able to observe anything once it's close to the sun. But while it's far from the sun, if you were to actually get up close to it, what you would actually see if you were to take an image that properly exposes the nucleus is that all of the jets would be just completely invisible, just because they're so faint compared to the nucleus. And so what happens is, in our case, the nucleus essentially outshines, we found the nucleus outshines many, many kilometers worth of the coma at that distance. And the other advantage that JWST has is, of course, that it is an infrared telescope. So we're not only seeing the scattered light, I mean, we have some images that are specifically targeting the scattered light, but we also have thermal images and looking in the mid-infrared. And in those cases, we're actually measuring, we can actually measure the temperature of the nucleus. And then it turns out the temperature of the nucleus physically is not quite the same as the temperature of the dust surrounding it. It's a little hotter just because the nucleus is essentially a surface that, well, the visible part of the nucleus is this flat surface, is a surface that faces the sun. So the thermal radiation, it can't radiate out in all directions. And we're unlike the dust, which is sort of free floating and out all in free space, whereas it has essentially 4 pi steradians of space it can radiate out its emission. And so the nucleus turns out to be quite a bit warmer than what the surrounding dust is. And so that sort of helps with the contrast as well. And we also, in addition, just looking at how bright it is, we could fit like a thermal model to actually essentially fit the black body spectrum of the nucleus itself, and found that the temperature is essentially the temperature we expect of the nucleus, which is warmer than the temperature you would expect of a free floating dust grain, which I think is reasonable evidence that we're actually detecting the nucleus itself and not just some artifact of the dust.
Thank you.
Okay. Bill, I wanted to bring you in on this. Bill has a lot of experience working with the SOHO Kreutz Sungrazers, and has, to my knowledge, has computed orbits for every single Kreutz Sungrazer since 2010. Is that right, Bill?
All the ones that have been published. There is, which unfortunately we haven't gotten very many of them published.
Well, okay. There are thousands that are not published, right?
Large backlog, but yes.
And you have not done orbits for all those yet?
Afraid not, no.
Okay.
Yeah. Still trying to come up with the problem is that doing them at that sort of scale is going to require a little bit of, we're going to have to up our game a little bit here.
Right.
It has helped a lot. Carl Badams has done a lot of really good work on getting us better data. I have a big leg up over the people in the past who have done this because from the examples Carl has sent me, I've just got a lot better data to work with. But our hope is that at some point we're going to catch up and be able to get data released for the several thousand objects that are pending. And it's a pretty exciting time to be dealing with sungrazers because there are new detectors coming on, replacing SOHO that will.
No, and I was looking at Brian Marsden's review article on sungrazing comets, which came out. It was in the Annual Review of Astronomy and Astrophysics. I think it was in the 2006 edition, and he kind of summarized the state of things regarding Kreutz sungrazers and sungrazers generally up to that point. And up to that point, I think it was 2004 was his cross section. At that point, there were 800 sungrazers found by SOHO, if I'm not mistaken, on that order, 800 or 900. And about 80% of them had Kreutz sungrazing orbits, which is really phenomenal. It's a lot of Kreutz sungrazing pieces, and I think Brian was really blown away by that. Brian had been working on the Kreutz sungrazer problem with the bright comets in the 1960s and 70s, and then Solwind came along in the late 70s and early 80s and found a few, less than a dozen, I believe it was, and then when SOHO went up in 96, 97, and it's still operating, right? SOHO's still running. How many do we have a figure? Is it like 3,000 or 4,000 sungrazing comets?
I think we passed the 5,000 5,000 SOHO comets.
Okay. And if his numbers extrapolated, he had at that time it was 80% were Kreutz Sungrazers, and of the
Mm.
20%, 80% of the 20% remaining were in three other new groups that were found. One that Brian
Yes.
identified called the Marsden group, one that our Mike Meyer found, the Meyer group, and Rainer Kroc, the Kroc group. In fact, Mike Meyer's group is the largest after the Kreutz Sungrazers.
Mhm.
And so it's very interesting. And I don't know in this set of data since 2010 what might we learn from that we hadn't learned before, because Brian died in 2010 and he was very faithful in doing all of the SOHO comets, putting them out with parabolic orbits, even though the arcs of most of them are really, really short because it's only what was visible in SOHO. And the SOHO resolution is quite small. I think in the smaller one, it's on the order of 20, 25 arc seconds, and it's more like 40, 45 arc seconds in the larger field. Is that right? So
That's about right, yes.
you don't have very good resolution. So basically, you have to just fit parabolas to it, and it's very painstaking, as you know.
And in a lot of cases, you not only have to fit parabolas, you have to say, we know that basically the Kreutz Sungrazers are dropping in from this point. We know where their perihelion is. So it winds up being an extremely constrained orbit,
Right.
With similar constraints applied to the other four main groups.
Right.
But it will be very interesting. I will not be surprised if still more groups turn out of this once we've got all of these examples to look at. So
Yeah, it's interesting. Mike, why don't you? I'd like to get you in here because you have some history with Kreutz Sungrazers, and not only in with regard to the SOHO comets, but also the history, the cometography you've done with Gary Kronk. What are some of your thoughts on all this?
Yeah, it's always a lot of suspicion connected with this. We have seen after quite a long time of only SOHO comets, recent years have seen quite a few bigger Kreutz comets, and every time when a new paper by Stenek comes out with some speculating of a bigger one coming maybe in the next few years, yeah, we are hoping for it. And there have been papers in the last decades always that there are certainly many unidentified Kreutz comets buried in historical data. And of course, because they are, if they are not too bright, quite hard to observe, not before perihelion, mostly for the southern hemisphere. And before, say, 1500, you won't have a lot of data from the southern hemisphere. Yeah, so the thing I take from it, they are much more frequent than we think. And in maybe when Brian did his studies, there were still big gaps in the timeline where he would say there was no sun crater there. Yeah, but those gaps, I guess, are not real because they haven't been identified. I'm currently waiting for the publication of a paper which has identified such a Kreutz comet and unambiguously. So we have found observation data positions from which we can derive an orbit and which shows it is a sun crater. And funny enough, it seems to be an object like Lovejoy. Yeah, so because maybe I hope I can do that. Let me share just one image. So I hope I have it here somewhere. Yeah, this one. So I don't know if you see it already.
Yep.
Yep.
Yeah. So what you see here is an image of the comet, this very comet. It's about 400 years old, and what is here called Draps ignea, or like burning trace or something like this. It looks like a tail without a head. You would even don't know where the head is or where the end is. Yeah. So and this is one example. So I just want to stop sharing. It will be contained in the paper there. It seems to be such a comet, which was seen just only as a tail after perihelion. The tail first very bright and then flattening out. Very, very similar to Comet Lovejoy. So and this shows, I guess, there are much more buried somewhere in the record books. But of course, we will never know unless we find, luckily, some data where we can prove it. And one last thing, if one asks me what I think what this comet will do, I won't give any comment. I'm prepared for everything for a daylight comet, which I still hope to see. I guess I reiterate it every meeting we have here. But I also have a look at the SOHO images just to follow it closely. So I'm really not sure. If I would bet some euros, I would say it will become a second Lovejoy, but I'm not really sure. So, yeah.
Yeah. The Nicholas, you had one of the reasons why I invited you in is I was a bunch of us were impressed with your simulations of comet tails, and you did a simulation or an animation projected for this comet maps. Is that right?
Yes, so I do this so people can prepare, and I can also prepare myself to what to do. And I have made several animations for several outcomes from pre-perihelion disintegration, Lovejoy type comet, a bit bigger, or even non-realistic IKEA Seki size, because now we know that it's not what we are going to see. And I have even made lately some that focus on perihelion also. So do you want to that I share some?
Yeah, sure.
Okay.
And we can put a link to your web page in the when I post the video.
Yeah, so let me share. So I need to share. I guess this time I need to share my screen, the whole screen. Okay, that and I have those here. What the program does is that it basically it's a mix of I try to input as much physics in the program, and there are a dense grid of synchros and syndines that is integrated, and then I calculate for each position parameters, like how it has spread, what is the exact angle, phase angle for the phase, and I try also to fit that before to observations to have something realistic. And once it's done, it's basically the same comet that is just rerun with just different parameters. Like when I do the Kreutz, I just change the H0 and all the geometry does the rest. So it's nothing input. So it's not true. It's just like a big interpolation when you change the way you see the comet. And that's one it's not on my website, but this one was made that I made lately with a very narrow angle. And I have the comet that comes here. It's in the case that it would be what I call the medium Kreutz, so something that survives perihelion, but is not too big. And then what we see that maybe what we could see in the future is the comet entering the coronagraph field of view. And then as it approaches, it vanishes like Lovejoy did. And then it goes behind the sun. Then for a very short time, it just emerges here. We don't know if we see really it on the other side of the sun here. And then it goes for a transit on the sun. And then for same as Lovejoy, at this time the comet, the full tail is burnt very quickly, so there is no tail, but as the comet recedes from the sun, a new tail forms. And then a few days later, it gets out of the glare of the twilight, and finally people might be able to see it. We could be able to see it for real.
Okay, so is this a projection as seen from the Earth?
Yes, it's seen from the center of the Earth.
Okay.
And I have the other one. Let me that maybe the Lovejoy size. I have many of them. Let me try back here. Right. I have the maps, and that's a Lovejoy case. So that's the headless case here. And in the headless case, so this is the same, but with a field of view that is larger. So the comet approaches the sun, so gets around the sun, and when it gets further, same as Lovejoy, it starts losing its head. It's basically Lovejoy that I have run through this geometry, and it appears at a much narrower than Lovejoy, and disappears slowly, and also much more slowly than Lovejoy because it appears more condensed on the sky because the Earth is near the orbital plane crossing, and also the orientation of the tail is a bit different, and then it disappears, just dispersing in the sky. So it's just to help and I think it helps people not to have unrealistic expectation. The best we can expect is something with a tail maybe 10 or 20 degree, but not something as huge as other Kreutz that we have had in the past.
Right. Well, we're going to learn a lot more in the next week, I guess.
Yeah.
We're getting close to perihelion, April 4th, and this is March 26th as we are doing this discussion. So we're a week and a half away, and we'll see what happens. Anybody else have anything they want to add?
Dan, I've got a couple of one comment and one question, if that's okay.
Yep.
It seems to me that looking at the graphs of the light curve that have been shown by people on here, that there's been a reasonable contribution to the data by amateur astronomers, and it's amateur astronomers that are going to be watching this video, so it'd be a good encouragement for them to see their data data produced by people working in their environments to be able to produce this information, and I think that's be quite encouraging for them.
Yeah.
Second off, it's related to what Casper was saying about the visibility of this comet at discovery, because it would be nice to be able to discover these Kreutz Sungrazers at large distances like this one has been. Is there any possibility that the Rubin telescope is going to pick up these Kreutz Sungrazers much earlier than we've been able to do in the past?
Well, I don't know exactly, because Rubin will be also surveying through the galactic plane, and then they'll have like what they call the northern ecliptic spur. So I don't know exactly what will happen, with Rubin, whether they will be able to discover them much farther out. I mean,
it would be nice to have some statistics from maps, possibly, of how much exposure time and how many hours of, observing that they needed to find this comet, and see if there's going to be any way that could be reproduced by other search groups if Rubin isn't going to be the one instrument that finds a lot of these type of comets.
Yeah, well, I know that the MAPS team, they have been extremely prolific for the past 5 or so years. In fact, I mean, they've been discovering comets every single year, if I'm not mistaken, either under MAPS or Maury Attard or Attard-Maury names. Yeah, I know that amateurs don't tend to have that problem of not being able to search in the Milky Way. Smaller fields of view, you don't reach as faint as the professional surveys. I mean, a comet comes to mind, discovered by my friend and coworker from CSS, David Rankin. He found a comet in the Milky Way from his backyard using his amateur telescope, because he knows that that in the Milky Way, a comet just could have an outburst. And in fact, he discovered that comet during an outburst.
When you look at another search team, say Borisov, most of his searches are in the northern hemisphere, near the North Pole, I think, aren't they? And he's been successful in finding comets there, but they're not going to be sungrazing comets.
Sorry, who?
Borisov.
Yeah.
I think he's mostly been looking at low elongations. That's one reason he found his interstellar comet. He was looking where surveys don't look.
That's the amateur technique, right? You want to look either close to the sun or in the Milky Way. if you're an amateur and you want to find a comet. I think the whole LSST thing is an interesting question. In the case of this MAPS comet, 2026 A1, it was found at 18th magnitude, right, in mid January. And Sam Dean's observations, he identified it in Atlas observations early January at 19th magnitude and mid-December at 20th magnitude, right? So it had brightened a couple of magnitudes in a month. Now you go back another month into November, you're down in the 22nd magnitude range. None of the current surveys really do that. Pan-STARRS can maybe barely get that. But I don't. Catalina doesn't do that.
Well, the bulk that we use,
right.
We go down to 23. Yeah, but the coverage is extremely limited.
Right. Whereas the LSST has a much bigger field of view, and it goes quite a bit fainter. So there's a chance we might get some of these Kreutz Sungrazers further out with LSST, but a lot of LSST we have to wait and see what's going to happen because they have a very unconventional way of doing things and not putting out data right away, apparently. So we'll have to see. They're supposed to be online sometime this year, starting to throw data at the Minor Planet Center. So we'll see how that goes. Any other thoughts, Joe? Do you have any concluding thoughts?
Not really. I could show a diagram of how the comet will look in the evening from the northern hemisphere, where it will be located.
Sure.
Just do a quick share.
Yeah. And also for those listening, a really good online planetarium program is called theskylive.com. You can go there and put in your own coordinates, and they have coordinates for comets like the 2026 A1. And so you can put in your time and see how this or other comets would be placed in the night sky for you.
This diagram shows from our St. Louis latitude of 38.6 degrees north what the horizon's at civil twilight when the sun is 6 degrees below the horizon shown in green, and nautical twilight when the sun is 12 degrees below the horizon. But you can see that it doesn't clear civil twilight until the evening of the 6th. These dates are for it's the universal time date of 7.0, which corresponds to North American evenings of the previous day. And the tail will be very slanted toward the horizon as we saw earlier.
Right. Sort of in the direction of the motion of the comet, right? In your diagram?
Correct.
The tail will be roughly, as Nicholas was showing in his diagrams there, the tail kind of precedes the head of the comet when you're post-perihelion. Okay. Anybody else have any other thoughts before we close up shop here?
So I might just mention one last thing is that mentioned before the two possible cases of it potentially this comet potentially disintegrating before perihelion, or it could make it to perihelion. One thing that some people might not be aware of is that in the case of a lot of SOHO comets that actually get very bright, they actually do so after they are essentially entirely disintegrated. And it's something that you don't usually see with a lot of normal disintegrated comets, because when that happens and the nucleus breaks apart into little bits and pieces of rubble, they just stay as inert rocks, and you just see the big cloud just sort of floating away, dispersing into an ever decreasing surface brightness blob. And that is pretty common for comets that are not sungrazers, or comets that don't get within about 0.1 AU of the sun. But the thing is, if you take that sort of dispersed cloud of debris and you bring it close to the sun, one of the first things that sort of leaches out of all of those rocks is sodium, which glows a very brilliant orange. And it's sort of one of the main things that makes a lot of these SOHO comets visible when they otherwise wouldn't be, is because of all this material that's sort of just vaporizing, all of this dust. When the dust is destroyed, it doesn't sort of vanish into nothing. It turns into gas, and that gas is briefly visible. And so even if we see this comet get destroyed within the next few days, and what we're looking at when it enters the coronagraphs is a pile of rubble, we should still expect it to get extremely bright, just because there's quite a lot of rubble, a lot more rubble than you usually get with the small SOHO sungrazers. So it should still get fairly bright, likely into, at least if you add up all of the light coming out from the entire chain of rubble, probably will still reach magnitude 0 or even low negative magnitudes. So something to be aware of, that disintegration doesn't mean that the comet is just gone instantly. It just means that it will be bright in a different way.
Right. So the comet's still being observed. It's getting closer to the sun now, going into twilight. We'll have a few more days. Our ICQ Comet Observations Facebook page has lots of observations of photos posted of the comet on a daily basis. You can check that out. And also, we'll probably all be watching the online coronagraph spacecraft images as the comet rounds the sun April 4th, April 5th. And we'll keep our fingers crossed that we'll have something fun to look at afterwards, right? So, all right. I want to thank everybody for joining us, all the panelists here. I